Beneath the thin breath of a dying sky, Mars lies still, a world carved in rust and memory. Its deserts glow beneath a pale sun, a light so distant it feels like the afterimage of warmth rather than its source. Every ridge and crater tells of motion long vanished, rivers that once carved their purpose through stone, oceans that may have shimmered under a young and forgiving sun. Now, only silence remains. Not the silence of death, but the silence of something waiting. For centuries, Mars has held its gaze upon us. Through the trembling lenses of early telescopes, it became both dream and reflection. A twin world that seemed almost alive. Astronomers traced faint lines across its surface and wondered if they were canals, the signatures of civilization. Others saw only illusions, the human mind desperate to find itself in the void. Between hope and disbelief, Mars became a mirror, showing not life, but the longing for it. And yet, the planet endures in quiet defiance. Beneath its frost, chemistry stirs. Beneath its dust, traces of ancient rivers glimmer in ghostlight. Strange gases rise and vanish in patterns that defy simple explanation. Perhaps Mars never died. Perhaps it sleeps, dreaming slowly beneath its iron skin. While we, impatient and uncertain, look for life in forms we can recognize. There is a question that lingers in that red silence, older than our telescopes, older than our doubt. What if the signs were already there? What if Mars once whispered its truth, and we, bound by expectation, simply refused to listen? In the dust of another world, perhaps something once breathed, or still does, and we, blinded by certainty, have looked away. It began with a shimmer, a faint red spark hanging in the black ocean of the night. Through centuries, that spark became an obsession. Mars, the wandering star, named for the god of war, had long been a symbol of distance and desire. It was close enough to tempt the imagination, yet far enough to remain beyond reach. For millennia, it was nothing more than a point of light, drifting among constellations that felt eternal. But then came the age of glass, and through the eye of the telescope, Mars began to speak. The year was 1877. An Italian astronomer, Giovanni Schiaparelli, sat beneath the dome of the Brera Observatory in Milan. The planet was at opposition, nearer to Earth than it had been in decades, glowing brighter than any star. Schiaparelli peered through his instrument, its lenses trembling with the turbulence of Earth's own atmosphere, and began to draw what he saw. Thin lines, straight and deliberate, crossing the face of the planet. He called them canali, channels. The word would soon be mistranslated in English to canals. In that mistranslation, a world was born, not one of dust and rock, but of vision and hope. Across Europe and America, newspapers whispered of a civilization on Mars. Canals meant intelligence, design, intention. Humanity looked skyward and thought, we are not alone. Among the believers was Percival Lowell, a wealthy astronomer from Boston, who would dedicate his fortune and his life to proving that Mars was inhabited. In 1894, he founded the Lowell Observatory in Arizona, a place where the thin air sharpened starlight and imagination equally. Night after night, he mapped the planet, tracing hundreds of intersecting lines, forming what he believed was an intricate network of canals stretching across the Martian surface. An irrigation system built by a dying race, fighting to survive as their world withered away. Lowell's words were poetic, persuasive, and filled with melancholy. He described a civilization of engineers, channeling the last waters of their planet from pole to equator, a grand act of defiance against extinction. It was not just science, it was myth reborn, written through the language of observation. The world listened, enchanted. The red planet had become a mirror of our own fragility. But as telescopes grew sharper, doubts began to surface. Other astronomers looked and saw nothing of Lowell's lines, only the subtle gradients of deserts and shadows, the illusion of patterns born from the human mind's craving for order. The canals dissolved into skepticism. And yet, the idea would not die. It lingered in the imagination of a century that was learning to dream in steel and electricity. Science fiction rose on its foundation. H.G. Wells' War of the Worlds turned Martians from distant neighbors into invaders. The Red World had entered human myth, its silence filled with voices of our own making. Then came the age of machines. In the summer of 1965, a small spacecraft named Mariner 4 completed a journey of nearly 228 million kilometers. Its mission was simple: to fly past Mars and capture the first close-up images of its surface. For centuries, humanity had stared through lenses and guessed. Now, for the first time, we would see. The images arrived as a series of grainy signals, transmitted slowly across the void, decoded line by line in a quiet room on Earth. As the first complete picture took shape, silence filled the room. Gone were the canals, the oceans, the ancient cities imagined by Lowell. Instead, the screen showed a world of scars, craters upon craters stretching to the horizon. It was a graveyard of stone, untouched for eons, the illusion shattered. The scientists watched in awe, but also in grief. The planet that had once seemed alive now appeared lifeless, not a twin of Earth, but its ghost. Mars was a world that had died long ago. And yet, within those frames of desolation, something subtle persisted. Among the chaos of craters, there were gentle slopes, valleys that curved with the signature of flowing water, channels not carved by hands, but by rivers long vanished. Geologists began to whisper, what if the dream had not been entirely wrong? What if Mars had once been alive, not with civilizations, but with seas, storms, and microbial stirrings? The debate ignited anew. New missions followed. Mariner 9 in 1971, the first spacecraft to orbit Mars, revealed a world far more complex than the barren moon-like sphere Mariner 4 had suggested. As dust storms cleared, the cameras unveiled vast canyons deeper than Earth's Grand Canyon, extinct volcanoes taller than Mount Everest, and what appeared to be ancient riverbeds frozen in place. The greatest of these, Valles Marineris, stretched over 4,000 kilometers across the equator, a scar so immense it seemed to divide the planet in two. Scientists stared at its depth and shape, wondering what force had torn the crust apart. Near the poles, white caps glimmered, frozen carbon dioxide, and beneath it, perhaps water ice. Mars had fooled us once with illusion. Now it began to haunt us with truth. It was not the living planet Lowell had imagined, but neither was it the dead rock that Mariner 4 had shown. It was something in between, a relic caught between vitality and decay. As the data grew, contradictions emerged. Traditions, spectroscopic analysis revealed minerals that only form in the presence of water, hematite, clays, sulfates, all geological signatures of a wetter past. Channels carved into plains looked unmistakably like dried river deltas. The landscape was fossilized motion. Something had flowed here. Something had evaporated. The idea of a once living Mars took root again, this time grounded not in imagination, but in evidence. Scientists began to suspect that billions of years ago, Mars might have been warm, wet, and wrapped in a thicker atmosphere, perhaps even hospitable. But then something changed. The planet lost its magnetic field, its air thinned, and the sun stripped away its protection. The rivers froze, the seas evaporated, and life, if it ever existed, vanished beneath dust and time. In that realization, a paradox emerged. Mars was both dead and alive, geologically quiet, yet scientifically restless. Every new discovery whispered of motion, chemistry, and memory. Methane in its atmosphere fluctuated without reason. Minerals on its surface recorded ancient reactions. Crater walls revealed dark streaks, possible traces of briny water that appear and fade with the seasons. Mars had become a ghost that refused to stay silent. In the decades that followed, every mission would carry the echo of that first whisper. Schiaparelli's lines, Lowell's canals, the dream that would not die. Each generation of instruments saw deeper, measured finer, questioned harder. The canals were long gone, but the longing remained. And in that longing lay the truth of human science, that even our mistakes can lead us forward. Schiaparelli's misinterpretation, Lowell's fantasy, they were not failures, but beginnings. They taught us to look closer, to question the illusion, to separate vision from evidence. And yet even now the line between them remains blurred, because perhaps the canals were not entirely wrong. Perhaps beneath the dust, networks of frozen water still stretch unseen, connecting craters like silent veins. Perhaps ancient streams once ran in the patterns Schiaparelli traced, their memory encoded in the topography of a dying world. Mars, it seems, has always spoken, in light, in shadow, in silence. But its language is one of patience, understood only through time. Now, with every passing year, as rovers crawl across its plains and orbiters scan its valleys, we begin to realize that the red planet is not just an object of study, it is a chronicle of becoming and loss. A world that might once have known warmth and rain, that might have looked upon its own skies and felt the first stirrings of chemistry that sought to become life. The first whisper of Mars through a telescope was not a lie, it was a translation of awe. Humanity heard what it wanted to hear, and in doing so, began to listen. Today, as new eyes, robotic and unblinking, wander across that horizon, the silence remains. But it is no longer empty. It is dense, layered, filled with the residue of forgotten water and the possibility of breath. A world that once seemed so familiar has become stranger with every discovery. And so, beneath the red horizon, Mars waits still, patient, secretive, half-remembered, watching as humanity, ever curious, leans closer, hoping once more to understand what it tried to tell us long ago. A planet that once whispered through glass now murmurs through data streams and spectral readings, through the hum of machines and the dreams of those who study them. And perhaps, in that convergence, between error and evidence, between imagination and truth, lies the first true conversation between two worlds. Mars spoke first. We are still learning how to answer. The year was 1976. The sky above Cape Canaveral shimmered with heat as the countdown began for one of humanity's most ambitious missions. For centuries, Mars had been the subject of imagination and speculation, but this time the dream was not confined to lenses or conjecture. This time, humanity was sending its eyes, its hands, and its questions directly into the Martian dust. The Viking program was designed not merely to visit another world, but to ask the most haunting question in science. Are we alone? Two identical spacecraft, Viking 1 and Viking 2, would journey through deep space to touch the red plains of Mars. They carried not just cameras and instruments, but something far more profound. The first direct experiments in the search for life beyond Earth. After a journey of 11 months, Viking 1 descended through the thin Martian atmosphere and landed safely on July 20th, 1976, the 7th anniversary of the Apollo 11 moon landing. As its legs pressed into the regolith, a cascade of dust settled over its gleaming frame. For the first time, human technology stood upon alien soil, ready to taste and test the chemistry of another planet. The experiments began almost immediately. The Viking landers carried a suite of 4 biological investigations designed to detect metabolic activity, subtle signs that microscopic organisms might be alive beneath the Martian surface. They were designed by teams of biologists, chemists, and engineers who had debated every possible outcome. Yet none of them could have predicted what was about to unfold. The first of these, the labeled release experiment, led by scientist Gilbert V. Levin, was elegantly simple. It mirrored a process used routinely on Earth to detect microbial respiration. A nutrient solution containing carbon compounds, marked with radioactive carbon-14, would be added to a small sample of Martian soil. If microorganisms were present and metabolically active, they would consume the nutrients and release radioactive carbon dioxide as a byproduct. The results would appear as a faint but measurable signal, a signature of life. On Earth, the test was so sensitive that even a handful of living bacteria in a teaspoon of soil would produce a clear, unmistakable response. When the experiment began on Mars, the team expected silence. For decades, astronomers had prepared for disappointment. The planet appeared too dry, too cold, too irradiated to host even the simplest biology. But what the Viking landers found was neither silence nor emptiness. Within hours of the nutrients' injection into Martian soil, the detectors recorded a sudden release of gas, a signal almost identical to that produced by terrestrial microbes. The needle on the monitor spiked. The data transmitted to Earth told a story that no one was prepared to hear. Something on Mars appeared to breathe. In control rooms across NASA, excitement flickered into disbelief. The initial signal persisted, then faded slowly, just as it would in a living culture when its nutrients are consumed. A control test was performed. The same soil sample, sterilized by heat, was retested. This time, there was no response. By all definitions, the result matched the pattern of biological metabolism. Levin's team celebrated quietly. They had followed every rule of scientific caution. The results had been replicated across 2 different landers in 2 separate locations on Mars. Everything fit, everything except one crucial detail. Another instrument, the gas chromatograph mass spectrometer, was designed to identify organic molecules, the basic chemical building blocks of life. To the astonishment of the entire scientific community, it found none, not a trace. This contradiction became the axis on which the entire search for life would turn. If no organics existed in the Martian soil, then the gas release could not be biological. Yet if the reaction behaved exactly as biology would, then what else could explain it? NASA's scientists were cautious. A non-biological chemical reaction, they argued, must be responsible. Perhaps the soil contained reactive chemicals, peroxides or superoxides, that destroyed organics while releasing oxygen when exposed to water. The official conclusion was drawn. The Viking experiment had not detected life. The result, though intriguing, was declared inconclusive. For many, it was a moment of disappointment, the quiet closing of a door that had opened too suddenly. The dream of finding life on Mars retreated once again into myth. But not everyone accepted the verdict. Gilbert Levine refused to let the question die. He was a scientist trained in precision and patience, but behind his calm exterior burned an unwavering conviction. For him, the data spoke plainly. The pattern of the reaction, the control results, the repeatability, all pointed to one conclusion. The experiment had done what it was designed to do. It had detected life. In the years that followed, Levin continued to defend his findings. He published papers, presented at conferences, and challenged the official interpretation. He argued that the absence of detectable organics might be due to the limitations of the instruments themselves. The Viking spectrometer, he noted, had a detection limit far above what modern instruments can achieve. If the organic molecules existed in concentrations below that threshold, the device would have missed them entirely. More importantly, subsequent missions began to find evidence that supported his doubts. In 2008, NASA's Phoenix lander discovered that the Martian soil contained perchlorates, highly reactive salts that, when heated, destroy organic compounds. This discovery offered a startling revelation. The Viking lander's process of heating samples before analysis may have inadvertently obliterated the very molecules it was trying to detect. Suddenly, the contradiction that had haunted the Viking results began to make sense. Life could have existed in the soil, producing the gas seen in Levin's experiment, and the same soil chemistry could have erased its organic traces before detection. The Viking enigma, long thought settled, was reborn. Scientists began re-examining the old data with new eyes. They noticed patterns that had been overlooked. The kinetics of the gas release matched microbial metabolism far more closely than any purely chemical process. The time-dependent behavior, the rate of decay, the thermal sensitivity, all aligned with biological activity, and yet official consensus remained cautious. Extraordinary claims, they reminded, require extraordinary evidence. To declare life on another planet based on a single ambiguous experiment would be to risk the integrity of science itself. But beneath that caution lay a deeper truth. Perhaps the fear was not of being wrong, but of being right. For if Viking had indeed found life, then the implications would be staggering. It would mean that life is not a rare accident of Earth, but a natural consequence of chemistry. It would mean that we were never truly alone, that biology is a universal language written into the atoms of the cosmos. Still, science demands humility before wonder. And so the data was stored, the conclusions tempered, the debate postponed. Levin's conviction remained unshaken until his death in 2021. In interviews late in his life, he often spoke not of vindication, but of curiosity. "We saw something breathe," he said, "and we chose not to believe it." Modern missions have continued to complicate the story. The Curiosity rover, launched in 2011, detected complex organic molecules preserved in ancient mudstones at Gale Crater. Molecules that the Viking spectrometer was never capable of finding. The Perseverance rover, now exploring Jezero Crater, has identified carbon isotopic ratios that some scientists argue could hint at biological processing, though the evidence remains inconclusive. Every new discovery seems to echo back to 1976, as if the Martian soil has been whispering the same answer all along, and we have spent decades learning how to listen. The Viking enigma has become a parable of science itself, the tension between evidence and expectation, between discovery and doubt. It is a story not only about Mars, but about the fragility of human certainty. For in the sterile laboratories of Earth, where data were interpreted through layers of caution and disbelief, a deeper question began to surface. Not whether Mars had life, but whether humanity was ready to accept it. The data were never just numbers. They were the faint heartbeat of a mystery that transcended the instruments that recorded it. The red soil of Mars had offered a reaction, a breath, a spark, and in return, humanity responded with silence. But silence, as history often shows, is not the same as absence. Today, as orbiters trace methane plumes across the Martian atmosphere and rovers uncover organic signatures buried in rock, the Viking results appear less like an anomaly and more like a prophecy. Each new mission adds a fragment of context to a story first written in the signals of 1976. And so the question lingers, suspended between science and belief. Did the first proof of extraterrestrial life arrive almost half a century ago, only to be buried beneath the weight of skepticism? In the quiet archives of NASA, the Viking data remain preserved, a digital relic of the moment humanity may have heard the first whisper from another biosphere. It is possible that Mars spoke then, in the language of chemistry and breath. It is possible we mistook that language for noise, but science, like the universe itself, has a memory. It waits for understanding to catch up with revelation, and perhaps when the next instrument touches the Martian soil, the silence will break once more. And the echo of that first experiment will be heard not as error, but as the beginning of an answer we were never ready to believe. In the frozen vastness of Antarctica, where silence wears a crown of ice, a small stone once lay buried, unnoticed, unremarkable, until the year 1984. It was lifted from the Allen Hills region by a team of NASA meteorite hunters, catalogued as ALH 84001. To most, it was one among thousands of space rocks that fell from the sky, fragments of a cosmic past scattered across the Earth's white deserts. But within this one, something extraordinary waited. A secret older than any civilization, older even than the Earth's memory of Mars. This meteorite was unlike the others. Chemical fingerprints inside its crystalline structure traced its birth to Mars, ejected millions of years ago when an ancient asteroid struck the red planet's surface. For eons, it drifted through the cold, airless dark until gravity drew it homeward, to a world that would one day call it evidence of something more than stone. In 1996, the silence broke. NASA scientists announced that, within ALH 84001, They had found patterns, tiny shapes, curved and hollow, nestled among carbonate globules. Under the magnifying gaze of the electron microscope, these forms looked hauntingly familiar. Ovoid, segmented, bacterial in outline. They looked, to the human eye, alive. The images flooded newspapers. The world held its breath. Standing before the cameras, President Bill Clinton declared that humanity might have found the first evidence of life beyond Earth. It was a moment charged with awe, the dream of generations rising from a single Martian stone. The headlines spoke with trembling wonder. Life on Mars, Martian fossils found in Antarctic meteorite. And yet, behind the spectacle, the scientific community paused. Awe, after all, is not evidence. As the dust of excitement settled, the microscopes returned to work. Teams across NASA's Johnson Space Center, Stanford University, and the British Geological Survey began their quiet interrogations. The shapes, could they truly be fossils? Could something so small, mere nanometers in scale, represent a biological form? Critics pointed to chemistry. The carbonates, they argued, could form through abiotic processes, heat, pressure, and the slow mineral weathering of time. The magnetite crystals found near the globules could arise not from metabolism, but from inorganic growth. And the tiny structures themselves were far smaller than any known terrestrial microbe. Too small, perhaps, to hold the machinery of life. It was a moment when faith in the seen collided with the discipline of proof. In the years that followed, debate burned quietly in laboratories. NASA's own teams conceded that the evidence was inconclusive. The shapes could be biological, or they could be illusion, patterns made by geology, masquerading as life. The story faded from the headlines, slipping into the quiet halls of uncertainty, where scientific mysteries often go to sleep. But beneath the skepticism, something persisted. The magnetite crystals, their purity, their uniformity, mirrored those produced by magnetotactic bacteria on Earth. Carbonate layers within the meteorite bore isotopic signatures that hinted at low-temperature formation in the presence of liquid water. And the textures within the stone, fractal and layered, whispered of slow, gentle processes, not the violence of sterile mineral growth. So the debate began again. Scanning electron microscopes, newly refined in the 21st century, returned to the meteorite's surfaces. What they saw reignited wonder, patterns of alignment, microtunnels, and spherical voids that seemed sculpted rather than formed. The arguments evolved, not into certainty, but into complexity. Perhaps, some suggested, life on Mars was not like life on Earth. Perhaps it was smaller, simpler, built on scales that defied our assumptions about what a cell should be. Perhaps the problem was not with the rock, but with the limits of our definition. And here the narrative of ALH 84001 turned philosophical. What does it mean to recognize life when it does not resemble our own? For centuries, humans have searched the cosmos with the Earth as mirror, expecting other worlds to echo our biology, our carbon-based logic, our fragile chemistry of water and oxygen. But what if Mars tells a different story? One where life, if it existed, chose a subtler path, etched in minerals rather than membranes, whispering through isotopes instead of words. The meteorite became a riddle not of biology, but of perception. NASA's astrobiologists began speaking less of life and more of biosignatures, traces that might indicate biological processes. Complex organics, isotopic fractionations, mineral morphologies. It was a vocabulary of caution, born from the scars of earlier overconfidence. Meanwhile, planetary scientists returned to Mars itself. The meteorite had offered one tantalizing piece of evidence. But could the planet's surface provide the rest? Orbiters like Mars Global Surveyor and Mars Reconnaissance. Orbiter scanned the terrain, finding ancient riverbeds, mineral veins rich in carbonates, and hematite deposits shaped by water. The same minerals that defined ALH 84001 now appeared scattered across the Martian crust, as if the meteorite was not anomaly, but echo. And yet, still, the silence. The meteorite lay in a sealed case, guarded by nitrogen and memory, while its meaning drifted between science and philosophy. In the early 2000s, new isotopic analyses showed that its carbonates had likely formed in a warm, wet environment, possibly near the Martian surface, not through volcanic reaction, but through interaction with liquid water. It was the kind of chemistry that life could have used. But could chemistry alone prove existence? The debate fractured the scientific community into camps. One side insisted that the features could all be explained through non-biological means. Another, led by scientists like David McKay and Everett Gibson, maintained that no single geological process could account for the totality of evidence: the textures, the magnetite purity, the isotopic composition, and the nanostructures themselves. Each finding seemed to both illuminate and obscure. At conferences, discussions turned almost metaphysical. If one could not distinguish a microbe from a mineral, then perhaps the boundary between life and matter was thinner than imagined. The meteorite forced scientists to confront an uncomfortable truth: that life may not be an event, but a spectrum. From chemistry into consciousness, from molecule into meaning. The question was no longer simply whether Mars once hosted life. It was whether we were capable of recognizing it if it stared back through stone. By the late 2010s, renewed technology offered sharper tools. Cryo-electron microscopy, nanoscale secondary ion mass spectrometry, and synchrotron-based X-ray mapping began peeling deeper into ALH 84001's microscopic landscapes. Within its carbonate globules, trace organic molecules, polycyclic aromatic hydrocarbons, were detected. Contamination? Possibly. But perhaps, like whispers from the past, they were remnants of an ancient biosphere that had once breathed beneath a warmer Martian sky. If so, ALH 84001 was not merely a relic, it was a messenger. Across laboratories from Houston to Tokyo, new generations of scientists re-examined the meteorite not to prove life, but to understand its language, to ask what patterns mean when they outlive their creators, to learn how life writes itself into stone and how time translates it. Each discovery carried both revelation and restraint. For every sign that hinted at biology, another layer of caution arose. The line between organic and inorganic blurred further, until the debate became less about Mars and more about us, about the way we interpret silence, the way we define the living. The meteorite still sits beneath glass, its surface matte and ancient. Around it, the air hums faintly, with the breath of clean room filters, the constant sigh of preservation. Scientists look upon it and see both promise and doubt. To some, it is the first message from a Martian biosphere long gone. To others, it is simply a trick of chemistry. But between these two truths lies the beauty of the unknown, a beauty that keeps the question alive. For in the end, ALH 84001 may be less a discovery than a mirror. It reflects not the certainty of life, but the longing to find it. It asks not whether Mars once lived, but whether our own science is ready to recognize life beyond the image of itself. And so the investigation deepens, from rock to reason, from fossil to philosophy. Somewhere in that sliver of stone, amid patterns of carbonate and magnetite, lies the story of a planet that might once have breathed. A story written in silence, preserved in ice, carried across space for 16 million years, waiting for a species still learning how to see. Above the red horizon, a pale sun drifts through thin copper air. The planet lies still, ancient, scarred, its surface frozen in the stillness of memory. Yet somewhere beneath the silence, something stirs, invisible, rhythmic, breathing perhaps. It begins as all great discoveries do, with a trace. In the early 2000s, powerful telescopes on Earth, those that had long watched Mars with the quiet patience of centuries, caught a flicker in its spectral light. Within the reflection of sunlight off the planet's atmosphere, a signature appeared: methane, a molecule of carbon and hydrogen, simple, fragile, and impossibly fleeting in the open air of Mars. It should not have been there. Methane, under the ultraviolet assault of the sun, breaks apart within centuries, sometimes decades. For it to exist on Mars now, it must be replenished. Something must be making it. On Earth, that something is almost always alive. 95% of methane in our own atmosphere comes from biological activity. The slow digestion of microbes in soils, the fermentation in swamps, the breath of life itself released as invisible ghosts into the air. But Mars was supposed to be dead, sterile, geologically silent. And yet here it was, whispering a chemistry that suggested otherwise. At first, skepticism held sway. Ground-based detections were delicate, uncertain, blurred by Earth's own atmospheric interference. But then came confirmation from space. In 2004, the European Space Agency's Mars Express orbiter, carrying the planetary Fourier spectrometer, detected the same spectral lines. Methane was indeed present, roughly 10 parts per billion in the Martian air. A tiny concentration, but enough to make headlines. The announcement rippled through the scientific world like a pulse from the planet itself. And then the question, what breathes on Mars? If the methane were geological, it could emerge from serpentinization, a process where water reacts with olivine-rich rock deep underground, producing hydrogen that binds with carbon to form methane. It was plausible, even elegant, but no known geological activity on Mars seemed active enough to sustain it. The planet's crust was ancient, cold, and mostly sealed, and so another possibility emerged. Fragile but radiant, that somewhere beneath the Martian surface, microbial life might persist, sheltered from radiation and time. Microbes feeding on hydrogen, releasing methane in slow, imperceptible rhythms. The theory carried a hum of wonder and of fear, for if Mars was breathing, even faintly, it meant that life had either survived its ancient cataclysm or had arisen independently in its own crucible of dust and frost. It would mean that life, as a phenomenon, was not a miracle confined to Earth, but a universal inevitability. But then, like all mysteries, the signal began to change. Year by year, the methane faded, then returned. Instruments would detect it one season, then find nothing the next. The plumes seemed to vanish and reappear with no predictable rhythm. In 2009, observations from NASA's Infrared Telescope facility suggested massive regional releases. Clouds of methane, tens of thousands of tons strong, blooming over regions like Nili Fossé and Syrtis Major. Then they would dissolve again into nothing. The pattern was chaos. When the Curiosity rover landed in Gale Crater in 2012, its onboard tunable laser spectrometer, part of the SAM suite, was tasked with measuring atmospheric gases. For months, it found almost nothing. The air was still. The methane seemed gone. But then, without warning, came a spike, 7 parts per billion. A sudden flare that lasted for weeks before fading again. The scientists stared at the data, unsure whether to believe it. Methane could not appear and vanish like that. Not in a dead world. It was as if something beneath the surface had exhaled, a single, momentary breath. Over the following years, Curiosity recorded more spikes. Some small, some intense. Always localized, always transient, and always around Gale Crater, a basin that billions of years ago had been a lake. A place where sediments told stories of ancient rivers and long-lost shorelines. The mystery deepened. In 2018, NASA formally confirmed the methane fluctuations. The seasonal pattern became visible. Low levels in the Martian winter, higher in the summer. Yet this was not the rhythm of geology. It was the rhythm of something that responded to heat, to sunlight, to the turning of seasons. Was it chemical or biological? If the methane came from the breakdown of buried clathrates, ice cages trapping gas within the soil, it might explain the seasonal release. But no clear mechanism could account for the intensity of the spikes. Mars was, by all known evidence, geologically dormant. And so, the more haunting hypothesis lingered, that the methane was exhaled by living cells, hidden deep beneath the regolith, surviving on chemical energy alone. Still, science demanded restraint. In 2019, the ExoMars Trace Gas Orbiter, designed with instruments far more sensitive than any before, failed to detect methane at all. The gas that Curiosity sensed at ground level seemed absent in the upper atmosphere. Contradictions piled up. It was as if the planet itself was toying with observation, allowing one probe to glimpse its breath, while another saw only silence. The debate grew fierce. Perhaps methane existed only in localized pockets, quickly destroyed by reactive oxidants in the atmosphere. Perhaps the gas rose and vanished faster than orbiters could track. Or perhaps, as some quietly wondered, the methane detectors themselves were being misled by some hidden factor, an unknown chemical masquerading as life SS shadow. And yet, the deeper the scientists looked, the more Mars refused simplicity. For even without methane, the planet displayed the chemistry of possibility: perchlorates in the soil, reactive compounds that could break down organics, ancient clay minerals that once held water. Complex organic molecules detected by Curiosity in 2018, preserved in the rocks like faint signatures of a forgotten age. None proved life, but together they spoke of a planet that had once been fertile, and perhaps, beneath its frozen skin, still was. The image of Mars changed again. No longer merely barren, it became a paradox. A world where absence itself seemed alive, where chemistry mimicked biology, and where the air carried whispers that came and went like ghosts. Theories multiplied. Some suggested the methane might rise through fractures in the crust, vented from deep reservoirs where ancient microbes once lived. Others imagined ultraviolet light breaking apart meteoritic organics on the surface, producing methane without life. A few dared to propose that Mars was still geologically active, that magma chambers far below the surface still seethed faintly, releasing gas through unseen vents. But none of these theories could explain the timing, the sudden, seasonal breaths. To those who watched closely, it was as though Mars was breathing in cycles, a heartbeat buried beneath kilometers of dust. Curiosity's instruments recorded it with precision. The small, regular rise and fall of methane concentration as Martian seasons passed. In summer, when sunlight warmed the surface, the methane rose. In winter, it disappeared. A pattern like respiration. And so, the old question returned, not as speculation, but as a challenge. If methane on Earth is almost entirely biological, could Mars be an echo of the same pattern? Could microbes, entombed in ice, awaken briefly with the warmth, exhale their trace, and sleep again as the cold descends? Some scientists dared to imagine a hidden ecosystem, one that never touches the surface, one that exists in the thin aquifers and briny pockets deep beneath the permafrost. In those dark havens, shielded from radiation, tiny organisms could survive as they have for eons, living on chemical reactions rather than sunlight. Methanogens, as they are called on Earth. On our planet, they thrive in volcanic vents, deep-sea sediments, and beneath glaciers, worlds without light or air. They feed on hydrogen, carbon dioxide, and minerals. They exhale methane. Their existence proves that life can persist in the most hostile of environments. And their chemical signature matches exactly what we see on Mars. Perhaps some whispered, Mars never truly died. Perhaps it simply fell asleep, waiting for warmth to return. And if so, then the methane plumes are not random. They are messages, the faint sighs of a planet remembering how to breathe. In the years since, the mystery has only deepened. Curiosity continues its vigil, still detecting sudden surges of methane that no model can fully explain. Perseverance, armed with more advanced instruments, has begun its own search in Jezero Crater, another ancient lakebed that once held the chemistry of life. The data remains elusive, but the question refuses to fade. Every spike, every anomaly feels like a heartbeat, a reminder that beneath the dust, beneath the frost, beneath the silence, Mars might still hold the secret humanity has long sought. Not a civilization, not even complexity, but persistence. The quiet endurance of life, in its simplest form. And so, scientists wait. They watch the winds of a distant world and listen for the faint chemical rhythms that rise and vanish with the turning of its seasons. They do not yet call it life, but neither do they call it death, because somewhere in that thin red air, methane still drifts, fragile, fleeting, defiant. A molecule that should not exist, yet does. And in its quiet persistence, it tells a story. That perhaps Mars, the planet long thought silent, is still whispering, not through words or motion, but through chemistry, through breath, through the language of the unseen. The story of a world that may still be alive. In the years that followed the discovery of methane on Mars, silence settled over the red planet once more. But beneath that silence, questions multiplied, quiet, relentless, and electric. The scientific world began to fracture, not from conflict, but from wonder. 3 theories emerged, 3 paths through the labyrinth of Mars, each carrying its own truth, its own doubt, and its own dream of what might still breathe in the dust. The underground life hypothesis. The first theory began in the cold light of reason, yet carried the warmth of hope. It was known as the underground life hypothesis, the belief that if life ever existed on Mars, it may not have died, only retreated. Mars today is a frozen desert, battered by radiation and stripped of its atmospheric shield. Yet deep below, a different world may persist, one hidden from ultraviolet death, one still touched by warmth. Orbiters and rovers have hinted at this secret realm. Beneath the desiccated crust, radar instruments like Sharad and Marsis have revealed subsurface echoes, pockets of denser material, perhaps ice, perhaps brine. In 2018, the European Space Agency announced a startling detection beneath the Martian South Pole, a possible lake of liquid water sealed under kilometers of ice. Cold, salty, and dark, but liquid nonetheless. In such an environment, microbial life could, in theory, endure. On Earth, extremophiles thrive in far worse places. At the bottom of Antarctica's subglacial Lake Vostok, microbes survive in oxygen-starved, pitch-black waters that have been sealed for millennia. In the Atacama Desert, in Chile, bacteria huddle within rocks, harvesting minute traces of hydrogen from the air. Some use perchlorate, a toxic salt also found on Mars, as both food and fuel. Astrobiologists like Chris McKay have built models around these analogues, imagining Martian microbes feeding on hydrogen and carbon dioxide, metabolizing slowly, perhaps 1 chemical breath per century. In such deep time, metabolism itself becomes a whisper. Life becomes geological. The idea is not poetic fantasy, it's chemistry. Hydrogen is abundant in the Martian crust. Perchlorates, discovered by the Phoenix lander, can lower the freezing point of water to nearly 70 degrees, allowing brines to remain fluid where pure water would freeze solid. If microbes inhabit these hidden aquifers, they might live in a slow subsurface biosphere, shielded from radiation, thriving in saltwater veins that pulse faintly beneath the permafrost. But if they are there, they are nearly invisible. No rover can yet drill deep enough. No probe has yet reached such depths. The search, for now, remains a study of shadows, methane plumes, isotopic whispers, and the faint exhalations of a world that may still breathe below. 2. The ancient life theory. The second theory reaches backward through time, to a Mars that no longer exists. It is called the ancient life theory, and it begins not with methane, but with memory. 4 billion years ago, Mars was blue. It had rivers that wound through valleys, deltas that spread like fingers, and lakes that filled craters with shimmering reflections of a sun less fierce than our own. NASA's Mars Reconnaissance Orbiter has mapped the relics of this era, the faint traces of river channels and shorelines that curve through the dust. Curiosity's instruments have detected clay minerals, the residue of long-lost water. And the Jezero crater, where the Perseverance rover now roams, was once an ancient delta, a place where life, if it ever arose, could have taken hold. Scientists believe that early Mars had a thick atmosphere, rich in carbon dioxide, warmed by volcanic gases and shielded by a global magnetic field. It was a habitable planet, perhaps not comfortable, but alive with possibility. Then something changed. The magnetic field collapsed. Solar winds stripped away the air. Oceans evaporated into space, and the surface froze. Radiation scorched what remained. Mars entered a long winter that has lasted for billions of years. If life had begun there, microbial, aquatic, fragile, it would have faced extinction. But extinction is not always immediate. Sometimes life adapts by disappearing. Perhaps like seeds buried in permafrost, Martian microbes retreated underground as the atmosphere thinned, finding refuge in aquifers or basalt pores. Perhaps they insisted themselves, dormant but not dead, waiting for warmth that may never return. Fossilized traces could remain too, microbial mats, stromatolite-like layers, or isotopic imprints left in sedimentary rock. Curiosity once found tiny carbon-rich inclusions in ancient mudstone within Gale Crater, tantalizing, though not conclusive. Perseverance's latest samples from Jezero show complex organic molecules, too intricate to dismiss as mere contamination. They are not proof of life, but they are echoes. Echoes of a chemistry that once danced closer to biology than any other place beyond Earth. This theory speaks to loss, to a planet that once held oceans and warmth and then forgot them. But in that forgetting, it may have left behind fossils of metabolism, trapped in rock layers older than any life still visible on Earth. It's a hypothesis both tragic and hopeful, that Mars may be dead, yet still carry the record of its brief pulse of life, a geological ghost preserved in red stone. 3. The false positive theory. The third theory is colder. It cuts through hope like ice through still water. Known as the false positive theory, it argues that Mars is, and always has been, lifeless. That every signal we interpret as biological is, in truth, the product of chemistry alone. Methane, in this view, can emerge without life. Ultraviolet radiation striking the Martian surface can drive photochemical reactions that split and rearrange carbon compounds from meteorites or volcanic gases. Static discharge in dust storms might create reactive intermediates that mimic metabolism. Minerals like olivine and serpentine can generate trace methane when exposed to water or CO2 at low temperatures. A purely geological process, no microbes required. And those tantalizing spikes of methane near Gale Crater? Perhaps they are simply bursts of trapped gas released from permafrost by temperature shifts or pressure changes. A frozen exhale, not a living one. Skeptics point to Curiosity's inconsistent readings. Plumes appearing and vanishing, measurements varying wildly from orbit to surface. Some suggest contamination or instrumental quirks. Others note that Mars's thin air and dynamic winds make precise tracking nearly impossible. Without correlation to known biological cycles, they argue, the data remains inconclusive, suggestive, but not proof. In this interpretation, Mars is not a sleeping world. It is a stage where light and dust play tricks, where molecules dance in mimicry of life. The universe, after all, has no obligation to make its chemistry simple. And in that complexity, illusion often wears the mask of hope. 4. Between theories. The mathematics of possibility. Each theory stands on its own foundation, yet none can claim certainty. The truth of Mars lies in the tension between them, a balance between science and wonder. Astrobiologists quantify this uncertainty through equations like the Drake equation, adapted for planets beyond Earth. They estimate habitability by modeling radiation exposure, atmospheric pressure, and the availability of energy gradients, the chemical disequilibria that life feeds upon. Mars, by these calculations, sits at the edge of possibility. Its surface is sterilized by cosmic rays, its soil laced with oxidizing perchlorates, its atmosphere too thin to protect against ultraviolet death. Yet just below that threshold, conditions improve dramatically. At depths of 2 to 5 meters, radiation drops by 99%. At 10 meters, it becomes survivable for microbial spores. At 1 kilometer, it becomes Earth-like. The mathematics does not decide whether life exists, it only maps where life could. And that map, though narrow, still glows faintly with promise. 5. Speculation, beyond our biochemistry. But the debate does not end with Earth-like life. Some scientists and philosophers of astrobiology suggest that our very concept of life may be too narrow, that we search for ourselves in the cosmos and mistake unfamiliar forms for absence. What if Mars hosts life unlike anything on Earth? Not carbon-based, but silicon-based, a biochemistry suited for extreme cold and dryness, where complex silicates act as structural molecules and energy storage systems. Or perhaps something even more alien, quantum metabolic systems, entities that exploit tunneling effects at molecular scales to sustain themselves in near-zero energy environments. Such speculation is not without grounding. Quantum tunneling is a known feature of enzyme activity on Earth, a ghostly phenomenon that allows particles to cross energy barriers they cannot climb. If evolution can exploit quantum mechanics once, why not again, under different skies? Perhaps life on Mars never ended because it never began in the way we imagine. Perhaps it is chemistry that learned to persist without biology, a form of self-sustaining complexity, balanced between reaction and rest, order and entropy, a living geometry beneath the ice, slow as stone, ancient as dust. 6. The human mirror. In the end, these theories are more than hypotheses. They are mirrors. They reflect our own understanding of life, resilience, and what it means to endure. Whether Mars is alive or not, it has already transformed our definition of what alive could mean. To study it is to confront humility, the possibility that life is not a cosmic rarity, but a natural consequence of chemistry, or the opposite, that it is so fragile that only Earth, against impossible odds, has kept its flame. In both cases, Mars becomes a teacher. It shows a universe where death and dormancy blur, where silence may not mean stillness, and where a frozen planet can still whisper questions about our origins. The search continues through orbiters, rovers, drills, and dreams. Each theory adds a layer to the mystery, like strata in Martian rock. Somewhere within that sediment of thought may lie the truth, not yet uncovered, not yet spoken, and so the story deepens. Mars remains neither alive nor dead, but suspended between both, a red riddle holding within its frozen veins the memory of oceans, the chemistry of persistence, and the possibility that life, once found, may never truly vanish. The red horizon of Mars is no longer only an image on a telescope's lens. It is now a landscape of footprints, not human, but mechanical, silent, and tireless. The age of robotic curiosity has begun. 1. The pilgrims of steel and code. Across the plains of Jezero Crater, a rover crawls slowly over dust older than continents. Its wheels turn in rhythms older than thought, pressing into soil untouched for billions of years. Its name is Perseverance, and within its titanium shell lies one of the most ambitious dreams in human history: to touch the memory of life beyond Earth. Perseverance is not a wanderer without purpose. Every movement is calculated, every pause deliberate. It is equipped with tools of astonishing precision: Sherlock, Pyxel, Supercam, and a suite of sensors designed to see the unseen. Sherlock, the scanning habitable environments with Raman and luminescence for organics and chemicals, studies rocks with ultraviolet light, searching for organic molecules that fluoresce like faint ghosts under the Martian sun. Pyxel, the planetary instrument for X-ray lithochemistry, maps the chemical makeup of rocks at the scale of grains of sand, tracing patterns that might reveal biological structure or mineral residue left by ancient microbes. Together, they perform a kind of geological surgery, peeling back layers of time. Each drilled sample is sealed in titanium tubes, small, immaculate vessels holding fragments of the planet's past. These cores are not yet homeward bound. They wait, half buried in the Martian soil, for a mission that does not yet exist: Mars sample return. the planned collaboration between NASA and the European Space Agency. If completed, it will mark the first time in history that pieces of another planet return to Earth. Within those samples may lie isotopic ratios that whisper of metabolism, traces of carbon chains that once formed cell walls, or silence, the profound silence of sterile stone. The rover's cameras, its microphones, and its lasers all point toward the same question. Is there, within this dust, a faint residue of life? Or is this planet's memory empty, its chemistry nothing more than echo? Each signal Perseverance sends across the void travels for over 11 minutes, a journey through the vacuum of space, a whisper of data that humanity catches like a prayer. And in those numbers and images, scientists see more than rock. They see possibility. Too, beneath the surface, the next descent. Yet the surface may not hold the answers. For all its brilliance, Perseverance drills no deeper than a few centimeters. If life ever survived on Mars, it may lie beyond reach, buried under layers of dust, salt, and radiation-proof stone. This is where another machine enters the story. ExoMars, a joint effort of the European Space Agency and Roscosmos. ExoMars was designed to go where no probe has gone before, beneath the surface. Its heart is a drill, capable of reaching 2 meters into the Martian crust, where radiation fades and ancient sediments sleep. There, in that cold shadow, might rest preserved biosignatures, organic compounds unspoiled by the ultraviolet sun, microfossils frozen in time. Its analytical suite, including the Raman laser spectrometer, reads the vibrations of molecules, deciphering their structures with almost musical precision. Every mineral, every crystal lattice carries a distinct spectral tone. In that vibration, the instrument listens for the resonance of life. Though delayed by politics and logistics, the ExoMars mission remains one of humanity's most profound ambitions. Not just to observe Mars, but to touch its memory, to reach into its deep red marrow and ask what story it still keeps. For now, Perseverance, Curiosity, and orbiters like Mars Reconnaissance Orbiter and Trace Gas Orbiter form a chorus of observation. Their data paints a complex picture: methane that flickers in and out of existence, hydrated salts that appear after dust storms, frost that condenses in dawn's cold. To interpret this, humanity turns again not only to instruments, but to imagination anchored in science. 3. The laboratories of Earth. Far from Mars, in quiet rooms filled with artificial light, scientists recreate the planet's cruelty. They build Mars chambers, sealed environments where temperature, pressure, and radiation mimic those of the Martian surface. Here, they test the endurance of life. Inside these chambers, bacteria from Earth face their most ancient adversary: desiccation, radiation, and salt. Species like Deinococcus radiodurans, famed for surviving doses of radiation thousands of times greater than lethal human exposure, are exposed to ultraviolet light and cosmic ray analogues. Many die. Some persist. A few adapt. Halophiles, salt-loving organisms found in places like the Dead Sea, endure in brine solutions that match the perchlorate-rich waters believed to exist on Mars. Their cells bend but do not break, their proteins forming shields against chemical decay. Even fungi, lichens, and cyanobacteria from Antarctica's McMurdo dry valleys have shown resilience when exposed to simulated Martian conditions. For weeks, they continue slow photosynthesis, their metabolism whispering just above stillness. They do not thrive, but they endure. These experiments reveal a haunting truth. Life, as Earth knows it, is harder to extinguish than once believed. It can wait in the dark, feeding on energy so faint that it borders on nothingness. It can hibernate in ice, in salt, in rock. And if such resilience exists here, might it not echo elsewhere, under the frozen soil of Mars, beneath Europa's crust, or within the mists of Enceladus? The laboratory becomes a kind of chapel. Inside it, the act of simulation becomes meditation, an attempt not just to test biology, but to understand existence itself. To recreate Mars on Earth is to build a mirror where humanity stares into the reflection of its own persistence. 4. machines that listen to silence. On Mars, there is sound. The thin wind sighs across craters. Dust moves like slow smoke. But in that near emptiness, Perseverance's microphones hear more than noise. They hear time itself. When the first Martian wind recordings arrived, they carried not just data, but presence. The sound of another world's breath, faint and raspy, filtered through alien air. It was a moment that rewrote the distance between planets. Scientists call it acoustic science, but it is also a form of listening, not just to air and dust, but to the invisible hum of chemistry. Instruments like Sherlock and SuperCam detect molecular signatures in frequencies of light and sound far beyond human perception. To them, the planet is not silent at all. It is filled with frequencies, whispers of minerals, flickers of carbon bonds, faint traces of isotopic imbalance. Each signal becomes part of a slow symphony of discovery. And yet, for all this technology, no unambiguous sign of life has emerged. The silence remains profound. It is a silence that feels intentional, as though the planet holds its secrets not out of malice, but out of patience. Perhaps life on Mars, if it still exists, chooses not to announce itself. Perhaps survival there means invisibility, a retreat into chemical stillness, a form of being that cannot be easily seen or measured. Or perhaps the universe itself guards its most sacred truths until curiosity matures into reverence. 5. The philosophy of waiting science, at its core, is an act of faith. Not blind faith, but the faith that patience will yield understanding, that observation will reveal meaning. On Mars, that patience is stretched across decades. Rovers do not rush. Orbiters circle endlessly, each pass gathering fragments of truth. The scientists who interpret their data may never see the results of their life's work. Many who dreamed of finding life on Mars are now gone, their questions carried forward by new generations. Yet this is how knowledge grows, layer upon layer, like sediment. Each layer preserves what came before, compacted by time, waiting for someone to uncover it. In that way, the story of science mirrors the geology of Mars itself. The red planet is not just a world of stone. It is a monument to persistence. Its valleys and ridges record 1 billion years of waiting. Its dust, fine as smoke, remembers oceans long vanished. Its silence, unbroken for eons, is not emptiness, but continuity. The patience of matter awaiting comprehension. 6. The human element. For the scientists watching from Earth, each new image is both triumph and reminder. Triumph, because the machines work, the data flows, the questions deepen. Reminder, because every pixel is still a boundary, a limit to what can be touched, felt, or known. Perseverance, curiosity, insight, the orbiters. They are all extensions of human curiosity, fragile and finite, yet filled with purpose. Their circuits carry not only sensors and algorithms, but the distilled longing of an entire species. No other endeavor reveals humanity's paradox so clearly, that a creature born of mud and sunlight, confined to one world, builds machines to search for others, that we listen for life among the dust, even as we struggle to preserve it here. And so, science becomes a kind of prayer, not to gods, but to the cosmos itself. A request for dialogue, a whisper to the void, asking, are we alone? 7. Reverence. The deeper the search goes, the more it resembles devotion. To study Mars is to stand before an ancient relic of creation, a planet that once breathed, perhaps still does, and waits for comprehension. Astrobiologist Nathalie Cabral once wrote that the search for life on Mars is also a search for humility, the understanding that the universe owes us no revelation. Discovery, she argues, may depend not on better machines, but on better questions. To find life, humanity must first learn to recognize it, even if it does not resemble its own reflection. And perhaps that is the true lesson of Mars. Not whether it is alive, but what its silence teaches about our own. Patience, wonder, reverence. The modern quest is not a race for evidence, but a meditation on awareness. Each rover's wheelmark across the Martian plain is a line written in dust, a scripture of persistence. Each drill sample is an act of listening. Each signal from the red world is a reminder that knowledge begins with stillness. For now, Mars keeps its secret. Its wind carries no voices, its soil no certainty. But the machines still listen, tireless, unblinking, moving through rust and silence, carrying the oldest human question through the void. And somewhere in that silence, in the faint hum of dust against metal, in the glow of ultraviolet against stone, lies the answer, waiting for the moment when humanity is quiet enough to hear it. The red horizon fades slowly into a deep violet hush. Mars turns its cold face toward the dying sun, and shadows stretch thin across the plains of dust and silence. The last light catches the rims of craters like ancient scars, burns briefly upon a frozen dune, then sinks, leaving the planet to its long night. Above it, orbiters drift quietly, their solar panels glinting like wings of glass. Rovers stand still in their fields of rust and stone, machines of human memory whispering through static to a sky they cannot hear. And somewhere beneath that frozen soil, beneath layers of basalt and time, lies the question that has followed us for generations. Did life ever begin here? It is a question older than science itself, older than telescopes or equations. It is the question of loneliness, not the loneliness of one mind, but of a species staring into the dark and wondering whether it is alone in the infinite. For centuries, Mars has been our mirror, a planet so near, so achingly familiar, with valleys carved by vanished rivers, mountains higher than any on Earth, and plains that once might have echoed with rain. Every discovery we've made on its surface has pulled us closer, not just to it, but to ourselves. When the Viking landers first touched down in 1976, humanity waited breathless for the first signs, the faint flicker of life in a handful of Martian soil. The instruments stirred, measured, blinked. For a moment, there was confusion, then silence. The results were inconclusive, uncertain, unsatisfying. It was as if the planet itself had chosen to withhold its answer. Decades later, the rovers arrived. Spirit, opportunity, curiosity, perseverance, each carrying our curiosity like a small ember through the cold. They found riverbeds carved in stone, sediments layered in the language of water, and minerals that could only have formed in its presence. The story was clear. Mars had once known warmth. It had once known flow. It had once known possibility. But even as the evidence grew, the silence remained. If life ever existed there, if tiny cells once breathed in that thin air, or microbes slept beneath the frost, they left no clear trace. Perhaps they died in the Great Drying, when Mars lost its magnetic shield and the solar winds stripped its sky bare. Perhaps they retreated underground into hidden aquifers of brine and shadow, waiting still. Or perhaps they never existed at all. And so, we search, not merely with machines, but with meaning. Each rock turned by the rover's arm is not just a scientific act, but a prayer of sorts, an offering to the unknown. Each drill into the Martian crust is a question flung across aeons. Was life inevitable, or was it a miracle? If we find proof, even a single fossilized microbe, a molecular whisper preserved in ancient clay, it will change everything. It will mean that life is not a fragile accident, not a rare spark in a dark universe. It will mean that biology is not an exception, but a rule, a pattern written into the chemistry of planets, a song matter sings when conditions are kind. It will mean that somewhere beyond the horizon of stars, other worlds may already be breathing, dreaming, waiting. The discovery would not make us smaller. It would make us part of something larger, a continuum of being that began long before us and will continue long after. But if we never find it, if every drill comes up silent, every crater sterile, then Mars will still speak, though in another tongue. For silence too has meaning. A lifeless Mars would not be a failure, but a teacher. It would remind us that existence is not guaranteed, that the thin thread of habitability can be broken by the smallest shift. A lost magnetic field, a fading sun, a storm too long. It would show us how precious Earth truly is, how rare the balance that keeps oceans liquid, skies blue, hearts beating. In Mars's desolation, we see not alienation, but fragility. Silence becomes a kind of presence, the voice of all that could have been, reminding us of what still is. The philosopher Carl Sagan once said that to study Mars is to hold a mirror to ourselves. In its red dust, we find reflection of our yearning, our restlessness, our endless need to know. We project our hopes onto its landscapes, our fears into its shadows. We call it lonely, but perhaps it only reveals our own solitude. Because in truth, Mars has never been lonely. It has been watched for centuries, by telescopes, by dreams, by generations of minds that could not look away. It has lived not only in space, but in imagination. From the canals of Percival Lowell to the fiction of Bradbury, Mars has always been alive. Not with microbes, but with meaning. When the first astronauts finally stand upon its surface, they will not just be exploring a planet. They will be walking into the oldest question we have ever asked. Each step will echo through time, a heartbeat in the dust of another world. And maybe, in that moment, Mars will look back. For what is exploration, if not conversation? We speak through our machines, and the universe answers in silence, in spectra, in data too vast for any one mind to hold. But hidden in that exchange is something more profound. The realization that the search for life is also the search for understanding what life means. Every mission we send, every signal we interpret, every hypothesis we test, all of it is guided by a hunger deeper than curiosity. It is guided by the need to belong. The stars are vast, but meaning is not measured in distance. It is measured in connection, in the fragile bridges between knowing and wonder. So what will it mean when we finally know? If life is found, the boundary between us and them will dissolve. We will no longer be the universe's only experiment. The great solitude that has haunted humanity since the first night of thought will break, and the cosmos will feel a little less empty. And yet, perhaps the greater revelation will come if we never find it, because then we must confront a truth even harder to bear, that we might be alone. That consciousness, so effortless within us, may be a rarity so fragile that it has only bloomed once. That the universe, vast, fertile, magnificent, has given rise to awareness only here, on this small blue world. If that is true, then every breath becomes sacred. Every leaf, every song, every heartbeat becomes a cosmic miracle. And our duty changes, from seeking others to protecting ourselves. In the mirror of Mars, we might finally see not what we lack, but what we are. A species capable of curiosity so deep it crosses planets. A species that builds eyes to orbit other worlds. A species that sends its questions farther than it can go itself. We are young, still learning how to listen. Mars teaches patience, the patience of geology, of erosion, of time measured not in centuries, but in billions of years. It teaches humility, that even the most advanced instruments can be confounded by dust and distance. And it teaches reverence, that some answers are not denied, but delayed until we are ready to understand them. As night deepens over the planet, the temperature falls to a silence colder than any sound. Thin winds move across empty plains, shaping dunes that no eye will see. The rovers sleep beneath a canopy of stars so bright they seem close enough to touch. And somewhere, in that endless stillness, lies a question still waiting to be asked again. Not by a machine, but by something more ancient. The human spirit. The camera drifts higher, into orbit. The horizon curves, glowing faintly at the edge. The sun flares once more behind the rim of the planet, a single bright line dividing night from day. Perhaps this is what mirrors do. They do not answer, but reflect. And in the reflection of Mars, we do not find aliens. We find ourselves fragile, searching, luminous. The narrator's voice softens, almost to a whisper. Perhaps the signs were never hidden. Perhaps the problem was never Mars. Perhaps it was always us, looking for life while forgetting what it means to be alive. The planet turns, the light fades, and the silence once more begins to speak.